Ever stood at the foot of a mountain? Or maybe even, hiked up one? It really makes you think, what on earth could have enough muscle to push something that massive up from the ground? You know what I mean?
It's impressive, right?
Totally. And that's what we're digging into today, mountain formation and how it's all tied to the Earth's constant but usually hidden movement.
It really is fascinating.
I've got a stack of diagrams and research here that gets into how the Earth's crust and mantle interact. It's like a slow-motion ballet down there. But instead of tutus, we've got tectonic plates crashing and grinding against each other.
And those not-so-graceful collisions are what give us mountain ranges, volcanoes, earthquakes. They're the ultimate sculptors of our planet's landscapes.
Right. And we all learned about the layers of the Earth back in school: crust, mantle, core, and all that. But what I always found fascinating was this idea of the lithosphere and asthenosphere. Can you unpack that a bit for us?
Absolutely. Think of the lithosphere as the Earth's rigid outer shell. It includes the crust and the uppermost part of the mantle. And here's the kicker. This shell isn't one solid piece. It's broken into those tectonic plates we hear so much about.
Oh, yeah, there's like a cracked eggshell floating on.
Exactly. A less rigid layer called the asthenosphere. It's still incredibly viscous, but over millions of years, it allows the tectonic plates above it to move and interact.
And what's driving that movement? It's not like they're just drifting around on their own, are they?
Definitely not. The engine behind all this plate tectonics action is the incredible heat radiating from Earth's core. That heat creates these massive convection currents in the mantle. Hot, less dense material rises, cooler material sinks, and this constant cycle creates a sort of conveyor belt effect that drags the tectonic plates along with it.
So like a cosmic slow cooker churning up the mantle and shifting those plates around. Makes sense why things get interesting where those plates meet.
Interesting is one word for it. Those plate boundaries are where we see the most dramatic geological activity. You've got convergent boundaries where plates collide head-on.
Like a geological fender bender, but on a massive scale.
Exactly. And the results are pretty spectacular. When two continental plates collide, you get these incredible mountain ranges like the Himalayas. They're still growing today because those plates are pushing against each other with incredible force.
It's an unstoppable force meeting an immovable object almost. But what about when an oceanic plate collides with a continental plate? I imagine it's a bit of a mismatch.
You're right. The denser oceanic plate usually gets forced down or subducts beneath the continental plate. This process often creates volcanic mountain ranges like the Andes in South America.
So we've got mountains being built from both kinds of collisions. That's wild. But what about those other plate boundaries? The ones where plates move apart or slide past each other? Do those create mountains too?
They do,
Uh,
but in different ways. When plates move apart in divergent boundaries, it creates space for magma from the mantle to rise up, cool, and form new crust.
right.
This process is constantly happening at mid-ocean ridges, which are essentially underwater mountain ranges.
So while we're hiking up mountains on land, there's a whole other world of mountain building going on beneath the ocean's surface. It really makes you realize how interconnected everything is.
Precisely. And then you've got transform boundaries, where plates slide horizontally past each other. Now, these boundaries are more known for causing earthquakes, but they can also create mountains over time.
So we've got our colliding plates building mountains upward, our separating plates creating underwater mountain ranges, and our sliding plates. Well, they're keeping things exciting, that's for sure.
There indeed. And all of this movement, all of this interaction ties back to that idea of orogeny, the geological process of mountain building. It's like a giant construction project with tectonic plates as the building blocks and forces like faulting and uplift as the tools.
Okay, let's unpack those tools a bit because they sound pretty intense. What exactly is happening when rocks fold, fault, and uplift?
Imagine pushing on a tablecloth from opposite ends. It starts to buckle and fold, right? That's essentially what happens to rock layers under tectonic pressure. They bend and fold, creating those wave-like patterns you see in some mountain ranges.
So those folds are a result of the Earth literally flexing its muscles.
Exactly. Now, sometimes that pressure is so intense that the rock can't bend any further, and it fractures, creating a fault. These breaks in the Earth's crust are what cause earthquakes, but they also play a role in mountain formation.
How so?
Well, along those faults, you can have blocks of rock that are pushed upward, creating fault-block mountains. The Sierra Nevada Range in California is a great example of this: huge blocks of crust tilted upward by tectonic forces.
So it's like the Earth is playing a giant game of geological Jenga, stacking and tilting those blocks of crust.
That's a great analogy.
Yeah.
And finally, we have uplift. which is simply the upward movement of Earth's surface. This can happen over broad areas, creating plateaus, or it can be more localized, leading to the formation of individual peaks.
And this uplift, it's all driven by those same tectonic forces we've been talking about.
Exactly. The collision of plates, the subduction of one plate under another, the movement of magma, all of these can contribute to the uplift of Earth's surface and the creation of those majestic mountains we see all around us.
So we've got our building blocks, our tools, and our driving force. But I imagine there are different types of mountains, just like there are different ways to build a house.
You're absolutely right. And that's where we'll dive in next. We'll explore the fascinating diversity of mountain types, from towering folds to fiery volcanoes and everything in between.
Okay, so we've got mountains being thrust upward, blocks of land being stacked like some kind of geological Jenga game, magma pushing its way to the surface. With all this going on, it's no wonder we have such a variety of mountain types. Where do we even begin?
Well, we can think of mountains like the superheroes of the geology world, each with its own origin story and unique characteristics. We've got our classic tectonic mountains born from the direct collision of those massive plates.
Like the Himalayas we talked about earlier, those would be the heavyweights, right?
Exactly. The Himalayas are a prime example of fold mountains formed by the intense compression of two continental plates. Imagine two rugs pushing against each other, their edges wrinkling and buckling. That's essentially how those majestic peaks were sculpted.
So it's not just about pushing upward, but also about the way the Earth's crust folds and crumples under pressure. You really start to grasp the sheer scale of forces involved.
Absolutely. And then you've got fault block mountains like the Sierra Nevada. They're formed when blocks of crust are literally tilted upward along fault lines. It's kind of like lifting one side of a cake. You get that dramatic steep slope on one side and a gentler slope on the other.
Interesting. So we've got mountains being folded, mountains being faulted. Are there any other tricks up geology's sleeve?
Oh, there's more. Don't forget about upwarped mountains, which are formed by broad, dome-like uplifts of the Earth's crust. Think of the Black Hills in South Dakota. They're not as jagged as the Himalayas or the Sierra Nevada, but they're still mountains sculpted by uplift over millions of years.
So it's not always about dramatic collisions or massive faults. Sometimes it's about slow, steady uplift that creates these unique landscapes. But what about volcanoes? They form mountains too, right?
Absolutely.
What?
Volcanoes are a whole other category. They're mountain builders powered by fire. We've got shield volcanoes like those in Hawaii with their gently sloping sides built up by layers of flowing lava.
Like someone pouring batter onto a hot griddle, creating those wide, pancake-like formations.
That's a great image.
Yeah.
Then you have the more explosive types like stratovolcanoes. They're built up by layers of ash and lava, creating those classic cone shapes. Think Mount Fuji or Mount Rainier.
And those are the ones that tend to grab the headlines when they erupt. But what about mountains that are carved out rather than built up? I'm thinking of those incredible landscapes you see in places like Yosemite with their sheer cliffs and deep valleys.
You're talking about erosional mountains. Those are formed by the relentless forces of wind, water, and ice, carving away at existing landforms. Think of a sculptor chipping away at a block of marble to reveal the masterpiece within. Erosion does the same thing, just on a much grander scale and over much longer periods.
So mountains are formed, they're shaped,
Yeah.
and they're ultimately worn down by these natural forces. It's a constant cycle of creation and destruction, isn't it?
Exactly. And that's what makes geology so fascinating. But remember, mountains aren't just geological wonders. They play a vital role in shaping our planet and our lives in countless ways.
Okay, now that you mention it, we can't just talk about mountains without talking about their impact on the world around us.
Exactly. Next, we'll delve into how these majestic formations influence everything from climate and weather patterns to the very air we breathe and the water we drink.
So it's not just about how mountains look, it's about how they shape the world around them, right?
Yeah, absolutely. Their influence on climate, for instance, is huge. Think about rain shadows. Have you ever noticed how one side of a mountain range can be lush and green while the other side is practically a desert?
Yeah, actually, now that you mention it, I have.
It's all because of how mountains interact with air currents. As wind hits a mountain, it's forced upwards. And as that air rises, it cools and can't hold as much moisture.
So one side of the mountain gets drenched.
Exactly. That's the windward side. Then the air moves over the mountain, and by the time it reaches the other side, it's like it's wrung out a dry sponge. That's the leeward side, where you often find those rain shadows and arid landscapes.
Makes sense. It's like the mountains playing weather god. And speaking of which, mountains are also key players in the water cycle, aren't they? All that snowmelt feeding rivers and stuff.
They're like giant natural reservoirs. Those high-altitude snowpacks slowly release water throughout the year, feeding rivers, replenishing groundwater. It's fascinating to think that the water we drink could have originated as snow on a distant mountain.
It really is. And all those different environments you find on a mountain, that must be a haven for biodiversity.
You've got it. Think about it. You can go from lush forests at the base to alpine meadows to rocky peaks, all within a relatively small area. And each of those microclimates supports a unique community of plants and animals.
It's like a mini continent in terms of the diversity packed into a small area.
Exactly. And we've only scratched the surface of how mountains influence our planet. We haven't even touched on their impact on human culture and history.
Oh, right. How could I forget? They've inspired artists and poets, challenged explorers, even shaped the course of civilizations.
For centuries, mountains have been seen as both obstacles and sources of inspiration. They provided natural barriers shaping trade routes and influencing the development of societies.
It's incredible when you think about it how these geological formations have played such a huge role in human history.
It all goes back to that interconnectedness. Everything from the rocks beneath our feet to the air we breathe to the stories we tell. It's all influenced by the incredible forces that shape our planet.
Well said. And this deep dive has really driven that point home. We started with this simple question about how mountains are formed, and we've ended up on this incredible journey, exploring everything from plate tectonics to climate change to human history.
It's a reminder that there's always more to learn, always another layer to uncover, especially when it comes to understanding the natural world.
So true. So to everyone listening, next time you see a mountain, take a moment to really appreciate it. Not just for its beauty, but for the incredible story it tells. A story that's billions of years in the making and still unfolding today.
A story written in rock and ice, wind and water. A story that connects us all.
Perfectly said. That's it for this deep dive, folks. Until next time, keep exploring.